I'd like now to invite Ruslan Salakutinov to the stage. Russ is an associate professor at Carnegie Mellon University and Cooley, the director of AI research at Apple, where, if history tells me, he will tell me absolutely nothing what Apple's doing. But he will tell us about his research. Russ, please.
Thank you. Thank you very much. It's exciting to be here. So what I'd like to talk about today is I'd like to give you a little bit of overview of some of the open questions, some of the toughest questions that we're trying to solve in the space of deep learning. And to Pedro's point, we are sort of belong to the tribe of connectionists. We're looking at a very exciting area of deep learning. And if you look at the space of the data that we have today, we're in the space of images, language, speech. We look at relational data. You look at scientific data. There is a lot of exciting things happening in the space of deep learning. Right? These systems are actually working surprisingly well. And if we look at the impact in the areas of speech, computer systems, recommending engines, language understanding, and I'm going to show you some examples of that in the talk today, and even in spaces like drug discovery, medical image analysis. But what I'd like to really focus on is I'd like to really focus on the open challenges, some of the key research that's taking place in our area, particularly in the area of deep learning. So the first area that I'm going to highlight a bit about is this idea of reasoning, idea of attention, and also building models that have memory. And I'm going to show you why it's important. Language understanding is another big area. Noah talked about it in his talk, and I'm going to show you some examples where deep learning is actually making a lot of progress. And deep reinforcement learning is another area which is sort of connected to reasoning and attention and memory, and I'm going to show you some examples of that as well. And also the areas of unsupervised learning, one-shot learning, and transfer learning. A lot of research is taking place, and we're making sort of little baby steps in all of these directions. But before doing that, let me just show you one success story. A couple of years ago, there's been a lot of work done in the space of caption generation. So here's the system. You can say, well, a car is parked in the middle of nowhere. It looks surprisingly well. It looks remarkably well, up until you see something like that, right? So you see an image here, and it says the handlebars are trying to ride a bike rack, or two men are playing frisbee in a park area. Right? So that's obviously not quite what we're expecting to see. And to that point, what we can do is we can build these models that have attention mechanisms. In this case, it's called visual attention. So this is an example of men riding a horse in a field. So you can see whenever you're generating the word man, you focus on the man. When you're generating the word horse, you tend to focus on the horse. And what these systems can do, they can at least tell us when the model is making a mistake. So here's an example, a woman holding a clock in her hand. And so whenever you're generating the word clock, you're focusing on sort of the pattern, so you see where the confusion is coming from. Or a large white bird standing in a forest. Obviously, you can see that the model doesn't quite get, there's actually a couple of giraffes there. But at least it gives us some impression of what's happening under the hood of the model. Now, let me get and show you how these ideas, attention ideas, can be applied in natural language understanding. Let me show you an example. This is fascinating, exciting developments happening in that particular space. So here's a particular data set, an example from a particular data set of who did what. You're reading, you have a context or a news story, arrested Illinois Governor Rod Blagojevich and his chief of staff John Harris on corruption charges and so forth. And now I set a question for you. I give you a query, right? And the query is President-elect Barack Obama said on Tuesday was not aware of alleged corruption by X, who was arrested on charges and so forth. So who is X, right? And obviously the answer is Rod Blagojevich. So how can we build systems, deep learning systems that can answer these questions? These are not easy questions to answer. You have to build a model that understands something about alleged corruptions and something about trying to sell Obama's Senate seat to be able to answer that question. And here's one particular mechanism for doing it. In this particular case, you can use something that's called a recurrent neural network to get the meaning of, or at least represent the document or sentences in the document. You're also using it to encode a query. And then what you can do is you can use something that's called element-wise multiplication model that tries to look at the dependencies between query and sentences in the document. I'm not going to go into the details, but a lot of these algorithms are sort of looking at both attention and something that's called gating. And then you're building these complex systems that, given a query, you're doing multiple passes over the document, so you try to figure out what is relevant information I should be pulling up from the document in order to be able to answer the query. And what's remarkable about these systems, and what I'm showing you here, is I'm showing you some of the attention mechanism that's taking place. So on the x-axis, you have a query. On the y-axis, you have part of the document. And what's important to notice here is that these systems, so the first layer of the model, is actually picking up connection between alleged corruption and Rob Blagojevich, right? At the second layer starts picking up the Senate sit and associating Senate sit with Rob Blagojevich. So it starts picking up on these clues about what is happening in the document as well as the query, and both of these evidences get collected and you can answer the question correctly. So some of the state-of-the-art systems are relying on these mechanisms of trying to associate what words you see in the query, what words you see in the document, and you're passing it through multi-layer representation in order to find the right evidence. This class of models also belongs to something that's called memory networks, and this is where the memory comes into play. This particular model was developed by Jason Weston, researcher at Facebook, AI research. And what happens here is that you're basically representing sentences as your memory. It's a very simple representation. So you're representing sentences, that's your memory, and then you have a query, and you're trying to retrieve the right part from your memory, the right part of the document. But unfortunately, these kinds of systems are still lacking a few things. So let me show you another setting, language understanding of trying something called broad context language modeling. So imagine I give you this text. Her plain face broke into a huge smile when she saw Terry. Terry, she called out. She rushed to meet him, and they embraced. Han, I want you to meet an old friend, Owen. Owen, please meet Emily. She gave me a quick nod and turned back to X. So who's X? Is the X Emily? Is the X Terry? Is the X Owen? So how do you make that reasoning? That's not a very easy thing to do, right? Even for us, like if you look at the whole passage, it requires a little bit of reasoning. And obviously, I hope that many of you see that the answer is Terry. But what we can do is we can do something that's called co-reference resolution. So we can try to figure out that Emily refers to her and she. And if you look at the last sentence, she gave me, you can associate she is the Emily, gave me is the Owen. And then once you realize that, you can answer the question correctly, right? So how can we build systems, you know, in a deep learning community that can actually do that? And that's not a very easy thing to do. So what can be done here is how can we incorporate prior knowledge? We have a passage. How can we get some of the natural language processing tools so that we can do co-reference, we can do dependency parsing? How can we get existing systems like Freebase is a knowledge-based system that looks at the entity relations, or WordNet that looks at the relationship between words? And how can we incorporate all of that knowledge into the deep learning, into these recurrent neural networks, so we can have a better representation of the text? And that's a big challenge. A lot of the work that's done today is not really using this extra knowledge. A lot of it is done by just looking at the text and trying to learn everything in an end-to-end fashion. Here's another example. Whoa. Something just happened. Oh, there it is. OK, we're back online. So here's another example. Mary got the football. She went to the kitchen. She left the ball there. OK? Obviously, I can model the entire sequence using recurrent neural networks. That's a standard thing to do. And in fact, if you do that, you can pretty much get close to the state-of-the-art results in a lot of different data sets that are out there. But then you can also do co-reference. You can say, well, Mary, she, and she, that's the same thing. So you can pass information forward, almost like having skip connections. You can also have hyponymy. So football and ball, they mean the same thing. So you can add another edge. And what it turns out is that you can represent this entire system as a way of having memory, explicit memory, where you're encoding connections between different entities. And you can basically incorporate everything into these recurrent models. And these kinds of systems give us state-of-the-art results on a lot of different data sets and allows us to incorporate a little bit of prior knowledge. Now, let me switch gears a little bit and show you how the memory can also be incorporated into reinforcement learning algorithms. And in fact, even though if you look at these systems, they seem different because these are different application areas, the underlying algorithms are exactly the same. And the underlying ideas are exactly the same. So what is reinforcement learning? It's actually a very exciting area of research that we see more and more developments. And the idea is that we want to learn behaviors. I give you a sequence of observations of action, or a sequence of observations, and then you want to convert these observations into actions. If I want to have an intelligent machine, I see, I act. Right? And the idea of reinforcement learning is that you take an action, you pass it to the environment gives you back the feedback or the next state, the next observation, and then there is also the reward structure that's in place that tells you where your action is good or not. In many cases, the rewards are just typically zero because nothing happens. In the space of deep reinforcement learning, we're basically building these deep neural networks that take observations. You can think of it as multimodal observations, which is images, sensor data, whatever that comes in, and you act, you produce some actions that you act on the environment. And now one of the exciting areas that's been taking place in our community is this notion of trying to learn external memory. Pedro talked about the model by basically saying a lot of structure or a lot of memory sits within these connections. And what we're trying to do here is we're trying to actually learn external memory. It's an external piece, and you're trying not just storing, but you're trying to learn what to store, and you're trying to learn how to retrieve what you're storing. And I'm going to show you some examples of that. And there was wonderful work coming out of Alex Grave and his colleagues at DeepMind on differentiable neural computer machines and neural Turing machines that tries to accomplish that within a deep learning context. But before that, let me actually show you some of interesting results. So there was a work done at Carnegie Mellon by two students, Devendra Chatbot and Lampo, that appeared in IIII 2017. And what they've done is they've built an RL agent without memory. Right? So I'm going to show you what happens here. So this is learning to navigate. So this is in a Doom environment. So after 5 minutes of learning, notice what happens. Get stuck in corners. Apparently getting stuck in corners is a very difficult thing to avoid. You don't have memory, you're just seeing a few frames. After 30 minutes, the agent actually is doing quite well in terms of navigating in the environment. But it gets stuck because it doesn't see the barrel, right? Now, after 2 hours of learning, this is what the agent does, and you can see that it's actually pretty good now in terms of navigating and collecting things. And everything is learned from scratch, right? There are no rules, there are no specific pieces that we're injecting. You're just training the model to say your observation are your frames, and your output is the sequence of actions. And now you can also navigate with random textures so that you can learn to navigate in new environments. So it does reasonably well, and then after that, you're ready to go and navigate in unknown maps or unknown environments. And this is also pretty interesting that this is the map that you've never seen before. And the remarkable thing is that these agents, again, there is no memory. It's mostly you just see some frames, and you're learning to act or you're learning to navigate. And what you can do is there was an interesting competition last summer, learning to play deathmatch. And it's remarkable what these agents can do, right? So here you're seeing that they're learning to play Doom. And they're actually pretty efficient. In fact, they've tried to play with an average human, and they can basically outperform a human, right? An average human, not a professional. And one interesting thing is that if you look at this agent, it's actually learned to crouch, because apparently crouching, you get shot less, right? So you have this reward structure where you kill agents, you get the reward. If you get shot, you get negative reward, and that's basically what you have. But again, let me come back to this notion of memory. How can we, these agents, they can't plan. They can't build strategies, right? So how can we actually try to get in that direction? So imagine that I show you the following example. It's a random maze with an indicator. And imagine that I tell my agent that, well, there is something called an indicator. If it's a blue indicator, you have to go to the green block. If it's a pink indicator, you have to go to the red block, right? And you get the negative reward if the agent doesn't find the right block, so it doesn't hit the right, or if it sort of wanders around and doesn't really find the target. Now, the interesting thing is that if I tell my agent these rules, then the problem is solved. The interesting thing is that what if I don't tell my agent? I throw my agent in a maze, completely random maze, and the agent has to discover. Something is called indicator. There's something that's called goal. So depending on the indicator, I go and I find the right goal. And what we can do here, the way that we're incorporating memory is that you have an observation, and what you do is you write your observations into memory, right? And then you also take an action. At the next time step, what you do is you're reading from memory the relevant information. What is it that I remember in the past so that I can also update my memory, but then also take the action. So you can see there is this building block that goes from memory to memory, and so it can learn what's going on. So here's an example of what the system can do. This is a blue indicator, and if you see the blue indicator, you have to go to the green block. What the model does, it finds the wrong target, and then backtracks. It knows that that's the wrong target to go to, so it goes back and tries to explore in this maze, and actually goes and finds the right target, right? And this is the case where we don't specify to the model that there is something that's called an indicator. It learns about the environment on its own. It learns about what's important, what you need to store, and how do you extract it from your environment. And imagine that in the future, what I'd like to do is I'd like to build these systems where you'll know what the right structure is, you know that there is something that you're storing, you're retrieving, you're interacting with a knowledge base, you're building agents that can reason, that can communicate, and interact with the environment. I think that's something that we will see more and more in the next 5 to 10 years. One of the stumbling blocks of these systems right now is that it takes a long time to train, a long time to learn these systems. So one of the open areas and the big areas is how can we learn from few examples? How can we learn from few experiences so that we can actually get these systems to get where they need to sort of make sure that we can learn them reliably. Because right now it's very brittle, and these systems are very brittle at this stage. So I'm out of time. Thank you.